Hi, Ben with Novolux Stereophonic. Got an interesting piece here on the bench today. This is a Krell PAM-1. This is a very early Krell preamp. And what makes it interesting is that it's configured in dual mono. So when we open this up later, we're going to see that it's split down the middle with an identical preamp here and here. And what that entails is individual volume and source selection for each side. So say we wanted to listen to Phono 2, we'd have to select both preamps on Phono 2. And then I'd probably adjust my left channel to my listening level and then bring the right channel up to the same gradation to match. So it's going to be interesting to see how accurate these gradations are and if this is a reliable way to get a balanced stereo image once this thing is all back up and running. We also have on the front indications for the power supply and the ability to flip the tape monitor in and out. If we look at the back, it has a moving magnet, moving coil phono stage with looks like variable gain and loading here on these little switches. We have one line level input labeled tuner and then a tape loop and the output. And it looks like that block is identical on both channels. So I'm guessing there's a single PCB that was designed and there's just two identical PCBs in here, which we'll see shortly. The power supplies plug in on an XLR connection here. And I know nothing about this piece besides what I've gleaned from looking at the front and the back panel on these power supply modules. I don't know if these are DC or AC, so that's one of the first things I'll be looking into is opening one of these up and seeing exactly what's inside. It might just be a transformer. It might be a very simple power supply with maybe a single filter stage, and then it might just be like a kind of a high ripple DC that's on this. So we'll look into that and kind of get an idea of how that runs. But again, I don't know anything about this piece. You're going to be learning stuff about this as I go through it along with me. So if that sounds cool, stay tuned and we'll get this thing opened up. Let's start out by taking a look at one of these power supply modules. So in the various pictures that I've found of these, they don't all look like this. Some of them are just in a regular aluminum case. This one has this fancy gold anodized heatsink on it, so I'm not sure what that's about. That makes me think that maybe there's some sort of voltage regulator circuit in here that creates some heat, but maybe it was just done for decoration. It makes it look pretty cool and industrial. So this is an American piece, so it's probably going to be American hex. I'm going to try 5/64 on these two screws and see if that's the ticket. Yeah, that seems to be it. All right, I think those are the only two screws on this thing. Let's see if this can pull out. So looks like a fuse in the power transformer. Okay, it looks like we have a bridge rectifier and a capacitor bank. This must be the common. And then it looks like there's probably a plus and a minus rail. And it looks like a resistor there. And that's probably just the dropping resistor for the LED. So there's really only one stage of filtration here. I think it's probably 4700 microfarad times 2, one for the positive rail, one for the negative rail. But what's worrying me already is these are ROE capacitors. A lot of these European capacitors just don't hold up very well over time, so I wouldn't be surprised if these were already bad. So the first thing I'm going to do is fire this up and see if we have a plus minus DC rail coming out of this thing on the XLR jack. Okay, so the first thing I want to do is figure out the pinout on this cable, and my assumption was going to be that pin 1 was going to be ground, as if it was an XLR jack, but the common on these capacitors here on the top is not there. It's actually on the middle conductor, which is probably the second most logical way to do this, where you have the connector in the middle as your common, and then the connectors on the outside would be your rail voltages. So I'm going to flip these meters both to measure DC volts and get them plugged in here on the power supply. Let's see, I need to get this reference to ground. Okay, so I have meters plugged in to the XLR connector here. You can see I have some charge on these capacitors. I'm just going to power this up on dim bulb on a variac, so I'm just slowly raising my voltage here, I'm giving it about 20 volts AC, and these are starting to even out. We have a plus and a minus rail, and it looks like there's no shorts. I'm not drawing heavy current, so I'm going to take this up. I'm going to take it up to about 110 volts. This isn't loaded, so it's going to overshoot a little bit. My guess is this is probably like a plus minus 24. There's around 110 volts. If I take it to 120, it's probably overshooting a little bit what it's supposed to do. These caps are rated at 25 volts. So yeah, I bet when this thing is running, it's plus minus 20, somewhere around there. So fundamentally, this power supply is working. I don't know how clean the DC is coming out of it, but at least it fundamentally makes the plus and minus voltages. So I'm going to go ahead and repeat this test on the other supply, see if that one's working, and then we'll just test one channel at a time of the preamp. It looks like there's no bleeder resistor on this supply, so this could cause an arc if I try to plug this in to the back of the unit while it has a charge on it. So I'm going to go ahead and just drain this off. That way when we plug it into the preamp later, I'm not going to get an arc when I plug the connector into that XLR input. All right, that's good enough there. Let's test the other one. So just like the other supply, I have a decent negative voltage here. And my theory is that the LED indicator that's inside of this box is connected to the positive supply. So when it's unplugged from the wall, the LED kind of drains off the positive supply, but the negative supply is probably just going to stay high and drain off much more slowly. So that's something to be aware of if you have one of these. If you plug in the power supply without it being connected to the preamp, that negative rail is probably going to be sitting high. So just something to keep in mind. All right, let's do the same test on here. I'm on dim bulb. I'm just going to slowly raise it. And since the negative supply is already charged, we're not going to see that move until the voltage gets above about 5.5 volts here, and then they'll come up together. So far, so good. And now we're seeing them equal out, nice and symmetrical. I'll do the same thing. I'll go up to 100 volts. And we should be around plus minus 21 there, I think is what the other one was at. That's 100 volts there. Let's go up to 110. Oh yeah, 110 is where it was at on the other one. So at 110 volts in, I have about plus minus 21, 22 volts. So these supplies look at least good enough to do a test with, but I really don't trust these ROE capacitors. So later, once I spec a replacement for those, we'll put those on the Sencor leakage tester and see if they held up. Looks like it's probably going to be the same thing here, 5/64 SAE. Here's a look at the chassis from the top down. So as I suspect, we have a divider in the middle and two identical boards. The only difference really is where the power supply voltages come into the back of the chassis. So let's take a closer look at one of these channels and look at some of these parts. Taking a closer look here, we have 4 devices mounted on heat sinks here. The numbers on these are 7818 and 7918. These are plus minus 18 volt regulators. So my guess, I haven't looked at the schematic yet, but my guess is that you have a plus minus 18 volts feeding the line stage and a plus minus 18 volts feeding the phono stage. These are NPN transistors that look to be pass elements in some sort of other regulated supply, so I'm not quite sure what that's about, but I'm going to try to get my hands on a schematic that we can look at. Let's take a closer look at the capacitors. So we saw that there were some suspect capacitors inside of the power supplies themselves, but there's some more local filtering here. And these brown ROE caps are notorious for failure. I'm going to be replacing every one of these in here. We can already see here that there's some cracking going on some of these. Once these devices crack, they start to leak their electrolyte and they always go bad. This is a replace on site capacitor for me, these brown ROEs. This axial might be okay, but that's going to get replaced anyways. But it will probably run, so I'm going to power this up on dim bulb. We'll actually feed a signal through it. But before we do that, I want to take a quick look at the controls up front. The volume controls in here are super smooth. I can tell kind of just by the feel of it, it probably won't need any cleaning. It looks like a pretty sealed up design that should have held up pretty well over the years. Brand on that one is Spectral. And then on this one, it looks like stack pull, so another really high quality switch. So Krell was using some excellent quality parts in here. These capacitors here that I don't like so much, we're seeing in a lot of hi-fi gear in the 90s, especially Levinson and Krell. It's just one of those things that back in the day, they didn't know that these were going to be failure-prone capacitors. They were good audio caps to use, but they just don't hold up over the years. I'm just going to start by powering up one side here. So I'm going to plug one of the power supplies into this board here, and I'm just going to ramp it up on the Variac and just grab a meter and check and see if these voltage regulators are working. I'm just going to clip onto the chassis here somewhere, and then I'm going to turn this on at that 110 volts or so. And one of the things I like about these ProbeMaster probes is I can put this little extension on that kind of takes away some of the contact area, so I have less of a chance of making a short when I'm probing around in here. Now, these devices are the regulators, and I'm expecting plus minus 18. So I did a little bit of probing around here already and figured out that these resistors are right on the rails. So if I go around here, it looks like I got plus 18, minus 18, and then this is the other set of regulators, minus 18, and plus 18. I'm not sure quite what's going on here on these what look like pass transistors. So I'll need to look at a schematic and see exactly what these guys are doing, but it looks like we have a plus minus 17 coming into here. So these must be after the voltage regulator. So not quite sure what's going on there. These points up here are feeding the front panel LEDs. So we're getting a couple volts for each one of the LEDs, and both of the indicators are on. So I've got a red and a green LED here showing that our plus and minus rails are active. So it looks like this is fundamentally doing what it's supposed to. So I'm going to feed a signal into the line stage and see if we can get a signal out of it. Okay, so what I'm doing here is feeding a signal from my Siglent signal generator into the tuner input, and then I'm coming from the output into my Sencor PA81, which is up here, and then we're just going to look at the signal on this oscilloscope. So let's get a test signal going in. It looks like I've got 1 volt peak to peak running. I've got tuner selected, and I can hear something. There is not much of anything coming out of there. I wonder if my tape loop is on. Let's see. That's better. So I must have been on the tape input there. So I was just getting bleed. Wow, that is clean. There's no scratchiness or anything happening on this waveform. So this potentiometer is like amazing. That's really nice. Let's see what the square wave response is like. It's looking pretty darn flat. I like it. So this channel fundamentally works, and this thing's super simple because there's no because it's 2 mono blocks. There's no balance control. You just adjust the levels independently for the left and right channel. So it's a really simple signal path. Let's feed a signal into the phono stage and see if the phono stage works. Okay, I'm now feeding my signal generator into an inverse RCA filter. So I'm getting a corrected waveform fed into this. So it's basically like I'm playing a simulation of a vinyl record with a sine wave and a square wave coming into this, and we'll see what that looks like. So I'm not sure exactly how the source selection works because it just says Phono 1 and Phono 2. I'm on MC. I'm going to assume that's Phono 1, and that seems to work. I'm going to see what happens when I go to Phono 2. Okay, I'm going to move the connector here over to moving magnet. And we can see that there. So let's go back here, Phono 1. And in an ideal world, I'd be producing a perfect square wave. This has got like a little bit of a ramp on it, so a little bit of high frequency that's happening there, high frequency boost, but it's not bad. So overall, this thing is looking like it fundamentally works. So let's fire up the other channel and see what this thing does in stereo. Okay, so on this side, the line stage and phono stage seem to be okay. On this side, line stage is fine, but there's something wrong in the phono stage. Luckily, I have a known working channel here, so I should be able to compare and diagnose and resolve that issue. I'm also going to completely replace all of the electrolytic caps in here because, again, these are known to fail parts. So I think I'll start with that just in case there's some weird issue going on with one of these caps and it's shorted or something and it's causing the phono stage to whack out. I doubt that's going to fix it. It's probably going to be a transistor or something in the long run, but I'll start with the caps because they need to get done anyways, and we'll go from there. Okay, I've gone ahead and recapped the channel that was having issues on the phono stage. So I replaced this axial electrolytic, which is the little blue guy down here. This cap was fine. It did have a little bit of ESR. It had about 3 ohms of ESR, where the replacement cap was about 0.5 ohms of ESR. So a little bit of ESR creep on there. And then for the brown caps, these all tested really good on the peak purple tester. So I've had these give false readings before with that tester where they'll show that they have good ESR and value. These all tested about 550 microfarad with less than 1 ohm of ESR. So normally that would be a pass on that tester, but I've been tricked by these brown ones in the past, and my guess is at least one of these has significant leakage, which may have been causing our issue. Because after the recap, the phono stage is working beautifully. So there was definitely some issue there, so that's what I'll look into next to see if we can track down one or more of these brown caps that may have some leakage at rated voltage. Another thing that I did while I was in there working on the board was replaced a overheated resistor. So this one, you can see it's got kind of a black band around the middle where it's been stressed, and the same thing was in the other channel. So it was probably just that there's a little too much voltage drop across that resistor, and the engineers didn't plan out properly for the long term how much heat that was going to dissipate. So I've upped the wattage on it. It's right here, and I've got it lifted off the board a little bit so that same issue doesn't happen again. After testing all of the electrolytics on the LC102, I didn't find any capacitors that had any significant amount of leakage. So it's still kind of a mystery what was going on there. Maybe there was a cold solder joint or something like that, and replacing all the capacitors kind of reflowed everything and got it working properly again. So next up, I will true up the other channels so that they're exactly the same, and then we'll rebuild the power supply modules. In case anybody's following along and thinking about recapping their unit, I have some warnings about replacing these brown capacitors. You kind of need some specialized tools and a little bit of practice to get these out without damaging the board. So this is a double-sided board, and the traces are kind of thin and very easy to lift, and a lot of these capacitors have traces on the top and the bottom. So I developed a special strategy for getting these out that's a combination of a couple techniques that I've used in the past. So I'm going to go over that now just in case anybody's removing caps on this board. It might save you from lifting some traces. I'm going to be replacing these two capacitors here, and this is a good example because we do have the double top and bottom trace thing going on here. So I'm going to flip this over and prep the joints on the back side before we pull these out. So the solder joints that I'm going to be working on are here and here, and here and here. And we can kind of see that the leads are bent over. So when these caps were initially inserted in the board, the leads came through straight and they were bent over before they were soldered. And that makes it challenging to get out. So the first thing that I'm going to do is remove the solder from the pads so that I can bend the leads straight again. It's really hard to pull out the capacitor if you have that friction from the bend working against you. And I don't know if I would try this with a solder pump or wick. It's better to have the electronic pump. And most of the time when you're dealing with a double-sided board, there's enough of a gap in the through hole that you can use a vacuum soldering pump and suck all the solder from the top side through the hole. But in this one, the tolerances are so tight that you can't get any of the solder that's on the top side back through the hole. So in this one, I'm starting out by bending these leads straight again, and then I'm going to put a ball of solder on this side and just heat up both joints simultaneously, and then I should be able to drop it right through the board. This one's got another bend in it. I'm just going to cut the top off of this one so that it's straight. All right, so next up, we'll start with this one. I'm going to put a big ball of solder on each joint. And then I'm going to lift this up and get my hand underneath so that I can grab the capacitor and tug on it. So I'll try to get this in shot here. Okay, I'm on it. And then what I'm going to do is heat up both joints simultaneously. get the solder to melting point on both sides of the board and just pull the capacitor out. Okay, it's out there, and some are easier than others. This one dropped out pretty good. And then what I'm looking for is to make sure that I don't have a pad or something connected on this side of the cap. So this came out nice and clean. All right, let's do the other one. Okay, again, getting my hand underneath the board. An iron with a little bit of a longer tip will work better in this situation, but this is just about right. And that one came out a lot easier. So we still have solder left here, so I'm going to go ahead and suck that out. This is the other cap that was pulled, so that came out nice and clean. All right, so now I'm just going to get the solder off of these joints. And there may be some left over on the other side. Before I flip this over, I'm going to prep the surface for resoldering, so I'm going to remove this flux. Okay, so that side's prepped. Let's take a look at the other side. Okay, so this is where the two caps were pulled from, and you can see I have solder sitting on this side of the board, so I need to clean that up as well. And this will help you better understand how, if you were just putting, just kind of desoldering from the back and you weren't melting the top joint, when you start tugging on that cap, you're going to lift those traces right out. So hopefully this, this little tip will help you not damage any traces. And this applies to other products as well. So if you're just watching and you don't have a Krell, but you're just interested, this is a technique that you can use to desolder capacitors from double-sided boards without causing trace damage. One of the nice things about having this symmetrical design is that I can use one board to reference the other. So when I pulled the capacitors from the other board, I would desolder 3 or 4 at a time, and then I would use the brown capacitors on this side to give me my polarity reference. And now that the other side is completely rebuilt, while I'm doing this one, I can look at the other completed board to get my polarity correct. So I'm going to insert these capacitors, and what I did is I measured ahead of time the lead length, so when I ordered the replacement parts, I could get parts that would fit right into the footprint of the old one. Okay, so these are sticking through the board here, and I don't want to bend these at all, because if somebody ever has to replace these in the future, I want to make their job nice and easy. So what I'm going to do is just tack one side of each of them on, and then from the other side, I'm just going to put my finger on the top of the cap so that I can bring the cap flush with the board. And then I'll visually check from the other side and make sure they're sitting where I want. And we're done. This channel has been reworked so that it's the same as the other one. I retested the phono stage in this one. Everything looks good. So moving on to the power supplies. So this is going to be a bit interesting to service. I think I'm going to start off by removing these 4 nuts and see if I can rotate this whole sandwich out to get access to the solder joints. If not, I might have to desolder the transformer or the LED wiring so that I can get access to everything. So it looks like these screws are falling out of the bottom here. So I just have to make sure that I keep track of all these little standoffs and stuff. All right, let's see. Oh, great. So I just rotated that 90 degrees and I should have plenty of space to get in here and replace these capacitors. Okay, let's see how these caps held up. Wow, that's pretty high. Not necessarily a bad thing in a filtering situation, but a little troubling. I don't know the spec on these. They might be like plus minus 20% or plus 40 minus 10 or something, who knows. Well, that one is a little bit lower than the other one. Okay, so most of them are around 5600 microfarad, and that one was really high. So I'm going to throw these on the leakage tester and see if there's anything that sticks out, and then we'll replace them. So it looks like all 4 of these caps tested great on all parameters. Capacitance, ESR, leakage, they are good. But they're only rated at 25 volts, and this supply seems to run around 22 to 23 volts, so it's kind of right on the edge. And with modern mains voltages sometimes going as high as 125 volts, it might be really close to the maximum rated voltage of this capacitor. So I'm going to be replacing these with 35 volt rated capacitors just to get a little bit more headroom, some safety margin on the voltage. So I'm going to go ahead and swap these in, and we'll see how it works. Okay, so this is interesting. On initial testing, I haven't powered it up yet, but I've got negative 1.3 volts and plus 1.8 volts. So that must just be the dielectric absorption on the new part. So I'm going to power this on and ramp it up. Just making sure I got my polarity correct. So I'm just ramping this up slow on the variac. They should both be equal now, so I'll hop over to the negative rail. Looking good. All right, I'm gonna take this all the way up to 120. So that's at 120 volts. So you can see those original capacitors would have been right on the edge at 120. Maybe a little bit lower once the circuit's actually running and everything's loaded. But still, if I go up to, let's say I've got 125 volt mains, which is common here in New York City. Sometimes it goes as high as 127. So you're really pushing the limits on those original parts. So there's minus 24.83, and then here's the plus rail. Looks good. All right, we'll do the second one. Initially, I thought that the dropping resistor here in the power supply that connects to the LED was connected to the positive power supply rail, but I guess it's connected directly to the AC line, so they're running the LED off of AC. So as soon as you unplug this unit, this LED turns off. So I think what I was seeing when I had that high negative voltage at the XLR jacks on these meant that somebody had either plugged these in recently to the wall without having them connected to the preamp chassis itself, or there was just dielectric absorption in the existing capacitors and it was just slowly building up a charge. So I just wanted to correct that. I think initially I said that this was connected to the positive DC rail, but that's not the case. I've got both power supplies recapped and connected. I'm testing the line stage now. And what I'm doing for this test is I just want to check the balance of the gain here. So what I did is I took the volume controls and set them each to about noon, so right around the 10 mark. And then I fed a signal in from my Panasonic here, enough to generate about 1 volt RMS. So I'm feeding 920 millivolts, which is like 9/10 of a volt, into the line stage. And then I'm getting almost exactly 1 volt out. Now, what I had to do to get these channels exactly matched, if we look at this, I've got the channels overlaid. To get them to match, I had to slightly tweak the gain controls. So the left control is just a hair under the 10 mark, and the right control is just a hair over. And I don't know if that's going to be related to differences in gain in the preamp stages or just how the control is mounted, because it's just on a set screw. I need to remove these controls to clean the faceplate and everything anyways, so when I put them back on, I'm going to try to line it up as exact as possible. So I've been working on the cosmetics on this unit. I took off the faceplate, polished it, polished the badge, the knobs, reassembled everything. And the last thing that I wanted to tackle was the LED brightness. So the red LED is far brighter than the green. I prepped to substitute in a different resistor value here. I was going to use my decade box. And not only did I connect on the wrong LED, but I accidentally had the box set to 0 ohms. And with no current limiting resistor, the full supply voltage went through the green LED and blew the top right off of it. So now I've got an LED missing that I'm going to need to replace. So while I'm doing this color balancing, I think what I might do is try a different color. There's no reason that this needs to be red and green besides keeping it historically correct. But a lot of the newer Krell stuff uses a blue LED. So I think it might be kind of cool to experiment with that. So that's what I'm going to try, a couple blue LEDs in there. I don't necessarily need a different color for plus and minus as long as the LED lights to show that both supplies are on. So I'm going to swap in some blue LEDs and do some experimentation with the values and see if I can get this looking how I want. So this is how the original LED lighting looks. And what I found is that it's more about the angle. So if we raise it up and get to a point where we can see them both head on, they look very similar. But when the unit is down, or you might have it down on a lower shelf, it's always going to look kind of funny. So I'm going to try to sub in the blue LED and do a couple different things. I want to change the depth because the red one sticks way out and then the green one's kind of recessed back. I think having it a little bit more recessed is going to look better. So I'm going to do some experimentation here and see what it looks like. Okay, I'm trying a couple of different things here. So I've got a blue LED installed here and I recessed it back a little bit, which I'm not completely sold on. I think I do like the dome of it coming out and you don't see the sharp edge here. But what I don't like is on the blue, I already have a lot of resistance on here and it's still super bright. This must be an ultra bright blue LED. So I'm either going to have to compensate further or go with a different LED. So I'm going to do some more experimentation and come back once I've figured something out. The problem that I'm having with the blue LED is that the lighting element in this specific LED is really far back and you can't really get it bright enough to illuminate the outside perimeter so you can see it from all angles without completely overpowering the head-on view. So if I take this down and we look at this almost head-on, it's just way too bright and it's going to be annoying. Plus, I don't think it really jives with the silver and the gold color scheme on this one. The only thing that I really like about the blue is because this one specifically is an ultra bright LED. I just turned off the supply. In the other ones, your red and green lights extinguish pretty quickly after you turn it off, but you might still have like 15 to 20 volts there. On this one, because it's an ultra bright, it takes forever for it to finally turn off. So the power supply has to get down to like 1 or 2 volts before the light finally fully extinguishes. So it's kind of nice as a visual indicator when it's safe to unplug the power supply cable, but it's not enough of an advantage. So I'm either going to go back to red and green or try something else. After a bunch of experimentation with different colors and resistor values, I settled on this here. So this is a frosted red and green LED. The original is over here in the left channel unmodified. You can see it's more of a precise point of light. And it looks fine if you're looking directly on, but the problem is when we go off axis, the green just disappears. And that's not the case with the frosted ones that I put in here. So the idea here is that this preamp's probably never going to get turned off once it gets put into use because there's no power switch. Once the modules get installed, this thing's just going to sit and idle. So I don't want something that's going to be overpowering in the room and annoying to look at. So this gave me kind of the best of both worlds, keeping it original for color, but making it, balancing the color so it's viewable from every angle and it's just a little bit more pleasing to the eye. So once I finalized the resistor values for this frosted LED modification, I came to 22K and 100K for the specific LED that I used. And when I went through my stash of generic 1% metal films, I didn't have the same type in both 22K and 100K. So I quickly checked my stash of just leftover resistors. I have a bin that's completely full. Bring it down here. It says mixed resistors, and it's just a bunch of Mauser bags from all the projects that I've needed very specific resistor values for. And I just so happen to have 100K and 22K in these brown mil-spec metal films that are used in the rest of this. So it's almost like this LED frosted conversion was meant to be. So I'm pretty happy with how that turned out. Here are all the parts that I removed from the Krell PAM-1 preamp chassis and associated power supply modules. Now I had this interesting experience earlier. I needed to jump back into this baggie to grab some screws, and when I opened it up there was an unmistakable stench of dead fish. And that is the telltale sign of leaking electrolyte in these brown ROE capacitors. When these are cracked and leaking and you go to remove them, the whole room will be filled with this stench of dead fish. So these things were definitely on their way out, and I'm glad I got those all replaced while I had this unit on the bench. After getting the faceplate and knobs all cleaned up and reinstalled, I first of all mounted them with the line down here all the way on. But then when I feed a signal into it and put this right on the 10, I was just slightly off. So I just tweaked this knob just the tiniest amount, and it looks like it's tracking pretty well now. So this is both of them kind of right on the 10. If we go down to 5, I mean, I'm sitting off to the side, so I can't get it perfect, but there's 5, still looking really balanced. I'll just go to kind of a random dash up here, and that's looking great. So this strategy of kind of setting your left channel first to the approximate level and then just matching the right channel to the same, I think it's going to work out in this piece and be super, super nice. So I'm happy with how this one came out. I'm going to install the bottom cover and we'll just do a little bit more testing before buttoning this thing up. I finished all the cosmetic work on the PAM-1 and now I'm just doing some verification at the bench. So this is the spec sheet from the manual, and we're looking at frequency response right now, 1 Hertz to 500 kilohertz with 0.1 dB variation. And I was unable to reproduce that, and I think they might have just been fudging the numbers here a little bit. There's not really enough information on the page to duplicate their results. So what I'm seeing here on the Bode plot, and this is showing amplitude here and phase here with respect to frequency. So if we're looking here, I've got 10 Hertz and then going up to 600 kilohertz. So when we run that sweep, it's extremely flat, very, very flat, all the way from 10 Hertz all the way out to around 100 kilohertz. Then it starts to roll off, and our negative 3 dB down point, 1, 2, 3, is at 100, 200, 300 kilohertz here. And then by the time we get to 500 kilohertz, we're at 1, 2, 3, 4, 5, 6 or 7 dB down. So it might be that this thing can produce frequencies up to 500 kilohertz, and maybe they're saying the 0.1 dB is audio band. So if we look at 100 kilohertz to 20 kilohertz, yeah, that's less than 0.1 dB variation there. So I think that's what they're getting at, is that in the audio band, you have less than 0.1 dB variation, and it can produce frequencies well out past 400 or 500 kilohertz. And then in the phase plot, we have extremely flat phase response, also to around 100 kilohertz, and then a slight deviation here. So that's probably just very slight differences in the components between the two channels. So that's how the Bodhi plot looks. Let's hook this thing up and do a THD test. The distortion specification of the PAM-1 is 0.005%. I'm feeding the low distortion oscillator from this Panasonic analyzer into the tuner input on the PAM-1. I've got the gain controls both at 10. And I've matched it so that I have about 1 volt RMS coming out of each channel. Now if I go over to the distortion measurement, we'll see I'm right around that 0.005% here, but this is THD plus N. In order to match what the spec sheet is asking for, I need to go into this mode, which measures just the distortion and ignores the noise component. So we can see the right channel is just slightly higher than the left, but still way under specification. This is at 1 kilohertz. If I change the test frequency to 20 kilohertz, the distortion will rise slightly, but we're still below that 0.005%. And then just to go to the bottom of the band, I'm going to flip this down to 20 hertz. This is going to take a while to calculate. And with regards to the last test we did on frequency response, I had the device plugged directly into the oscilloscope, which is loaded at 1 meg. I don't know if that would affect it or not. There's just not enough information on the spec sheet to say what the loading conditions were. It just says 1 hertz to 500 kilohertz. So I did my best with what information they gave me, but overall the frequency response was very good. At 20 hertz, we can see our distortion is extremely low. So this has even lower distortion and low frequency. One of the interesting things that I learned from the owner's manual is this actually operates as almost a Class A audio amplifier. So we're going to look inside of the unit next and take a look at where that might be happening. If you remember when I initially opened up this device, I was a little bit confused at the voltage readings that I was getting off of these transistors. But after reading the manual, I think I've got it figured out. So they claim that the preamp operates as basically a power amplifier, and it has extremely low output impedance and a high voltage output. So the spec sheet claims it can do 15 volts and 10 ohms, which I believe is 15 volts RMS. And this heatsink gets extremely hot. So I think these two transistors are biased in Class A, and that's actually the output. So it's almost like a small Class A power amp driving the amplifier that's going to be connected to this. So it's a really interesting design. So anyways, I think that's what's going on with those two transistors, and just another reason why this is kind of a unique, cool preamp. Because this is a very early serial number PAM-1, it has different boards than the later version, and I'm having some trouble deciphering what all of the internal and external adjustments do. So these are the notes for the phono stage from the owner's manual that I can find online, but I'm pretty sure this is just for the late serial numbers. And this might also explain why I'm not able to kind of meet some of the specifications on the data sheet. I think maybe the old boards are specified slightly differently, or maybe there's a filter or something that's applied on these that got removed in the later version, so they have better frequency response. I'm not really sure. So if somebody has a copy of the owner's manual and would be willing to share some of the information from what was documented for the early serial number, that would be super helpful. But this is kind of what I found. I just jotted down some notes on my observations and measurements to kind of decipher what's going on in here, but I'm not 100%. So it seems like this control here changes the loading for the moving magnet section with these load resistors here, depending on the combination of the switches. This, I think, adjusts moving magnet gain, but that one I'm not 100% sure on. And then this affects MC gain. What did I write? MC affects gain on all levels. So this just changes kind of the gain when you're using the moving coil input. And then I have just some notes down here for what the medium, high, and low switch on the back, what it's loading the MC input at. So that's just some notes that I took on there. I just wanted to get this out in the public, so if somebody's trying to adjust this or figure out what these are doing, at least this might be a starting point. But again, if somebody has official Krell documentation on super early serial number PAM-1s, it would be interesting to see that in the comments. That does it for the Krell PAM-1. This was an extremely fun and interesting project. I'm super glad I took this one on. If you're interested in this type of content, I encourage you to subscribe, and there'll be plenty more to come. So we'll catch you on the next one.